Imagine waking up on a random Saturday morning, you're pouring your coffee, and you get an automated alert on your phone from your cloud provider.
Always a great way to start the weekend.
Right. And you check it, and you haven't spun up any new servers, you haven't added storage, your user base hasn't even spiked. But overnight, your company just got billed $2,800.
Wow.
Not for compute power, not for machine learning, literally just for the privilege of moving your own data from point A to point B.
Yeah, I mean, it is the ultimate invisible hemorrhage in modern IT. And, that specific $2,800 scenario,
Yeah.
that isn't even hypothetical.
Wait, really? That is a real number.
Oh, yeah. It is pulled straight from one of the case studies we are looking at today. It was this mid-sized data analytics firm. They just had this daily automated job exporting about 50 gigabytes from Google BigQuery over to an external business intelligence tool.
Okay, 50 gigs. That doesn't sound too crazy.
Right. Initially, it wasn't. It cost them maybe $180 a month.
Yeah.
Basically a rounding error for them. But as their client data grew, that silent automated background pipeline just ballooned.
And nobody noticed.
Not until it was consuming a quarter of their entire monthly cloud budget. Because, nobody checks the egress line item until it is on fire.
Which is exactly why we are doing a massive deep dive today to demystify this whole phenomenon. We are breaking down cloud data egress fees.
And we have got a huge stack of sources to navigate this with. We are pulling from the official pricing architectures for AWS, Azure, Google Cloud.
We've got engineering teardowns from Cast AI, Cloud Optimo, Backblaze.
Plus some really deep architectural case studies on edge computing from AWS and RealPars, research on video compression like AV1, and some truly brutal real-world survival stories.
From scrappy startups all the way up to massive industrial manufacturing giants.
Yeah.
Because this hits everyone.
It really does. And the material here is so crucial because we are not just looking at billing dashboards. We are doing a forensic dive into the actual architectural decisions, the code-level choices that make these bills explode in the first place.
And there's this recurring theme in the engineering blogs that I love. They call it the Hotel California rule of cloud computing.
Yes, such a perfect analogy.
Right. Your data can check in anytime you like, and the ingress is absolutely free, but man, it costs an absolute fortune to leave.
It really is designed that way.
So whether you are a CFO trying to figure out why your cloud bill jumped 40% last month, or you are a developer building a global app, our mission today is to equip you with practical strategies to, architect your way out of this trap.
But to stop the bleeding, we have to actually define the network boundaries first. Because a lot of people misunderstand what egress actually is.
So how do we define it?
Simply put, egress is data leaving a cloud provider's network. The big trap is that most organizations assume leaving the network only means a user downloading a file over the public internet.
Right, like me streaming a video or downloading a PDF.
Exactly. But internet-bound traffic is just the tip of the iceberg. The major cloud providers also charge you for moving data across their own internal geographic boundaries.
Wait, so even if it never touches the public internet?
Oh, absolutely.
Yeah.
Every time data crosses an invisible line on their map, the cash register rings.
So if I have a database in North America and I'm backing it up to Europe?
You are paying for every byte of that transatlantic movement. But it gets even more granular than that. You actually get charged when data moves between different availability zones, or AZs, within the exact same city.
Are you serious? Inside the same region?
Yep. If your app server in Zone A queries your database in Zone B, they are taxing that payload.
Looking through the sources, there is this huge debate about why they charge for this. Because the cloud providers, they always point to the physical infrastructure, right?
Yeah, they argue the cloud isn't magic. It is thousands of miles of fiber optic cables.
Yeah.
Like Microsoft literally funded a 4,000-mile undersea cable from the U.S. to Spain.
Which is an incredible engineering feat.
It is. And maintaining the largest private networks in human history costs billions of dollars. So their argument is that egress fees are just how they recoup those capital expenses.
Okay, I respect the infrastructure argument, but the sources push back so hard on this, they basically call it a hostage situation.
Which is fair, honestly.
Because if the physical cable is the reason for the cost, why is data going into the cloud universally free?
Right. It makes no physical sense.
If I upload a terabyte from my office to AWS, it uses the exact same physical glass, the exact same routers as data coming out, but it is totally free.
From a physics standpoint, Inbound and outbound traffic load the infrastructure the exact same way. The free ingress model is just an incredibly aggressive business strategy.
It gets you hooked.
Exactly. It lowers the barrier to entry. They want to ingest all your operational data to establish what the industry calls data gravity.
Data gravity. I love that term.
It is so accurate, right? Once you have petabytes of data anchored in their ecosystem, those egress fees become this massive wall. It is an incredibly effective vendor lock-in mechanism.
Because moving your own data to a competitor's cloud would literally bankrupt you.
Right. It is a nightmare for the consumer. And the scary part is how it scales. The sources talk about this compounding growth effect.
Which means it doesn't scale linearly, right?
Exactly. This blindsides CFOs all the time. A finance team will say, well, we expect our user base to double this year, so we will just double our egress budget.
But that math doesn't work out.
Not at all. It is fundamentally flawed. Because as your app matures, you aren't just adding users. Those users are interacting more deeply.
Oh, I see. They're using heavier features.
Yeah, they're downloading higher-res images, triggering more background syncs, hitting your APIs way more often.
Like that SaaS startup in the case studies, their egress hit $3,500 a month. That was 40% of their compute costs.
Just from serving image assets.
Just images. They saw a 10x increase in daily active users, but their network costs jumped like 15 or 20 times.
Which perfectly highlights why egress is the most unpredictable line item in an IT budget. Traditional software is deterministic.
Meaning you know what you are going to pay.
Right. You buy a Microsoft 365, the per-seat license cost for the year. Even cloud storage is pretty predictable. But egress, it is completely volatile.
Because you can't predict exactly what your users are going to click.
Exactly. It is driven by end-user behavior.
Yeah.
And if you try to throttle it, you degrade the user experience. Plus, it is driven by automated background processes that engineers set up and just forget about.
Like the manufacturing company doing the disaster recovery tests.
Oh, man, that story is brutal.
It is. It's an industry best practice to test your backups. So they spin up a secondary environment, they restore 15 terabytes of their own archived data just to make sure it works.
Being responsible.
Being responsible. And the reward was a surprise $1,200 bill just for moving their own data across the network during a safety drill.
It is punishing, which is why we really have to look at the actual pricing mechanics. If we want to fix this, we need to understand the fee structures in the cloud wars between AWS, Azure, and Google Cloud.
Let's lay it out. What is the baseline damage for just sending data out to the public internet?
Well, the big three are surprisingly synchronized here. They use tiered pricing. They usually offer this microscopic free tier. AWS and Azure give you the first 100 gigabytes per month for free.
Which is nothing.
It is literally nothing. A modern enterprise app burns through 100 gigabytes before lunch. Once that is gone, you are generally looking at 8 to 12 cents per gigabyte for outbound internet traffic.
8 cents sounds like a rounding error.
It does until you are moving petabytes. But you mentioned geographic boundaries earlier. That is where it gets crazy.
Right, the cross-region stuff. How bad does that get?
So moving data between those availability zones in the same region is usually about 1 cent per gigabyte.
Okay, 1 cent.
Yeah, but in a microservice architecture, millions of 1 cent database queries add up fast. But the real shock is routing across regions.
Like sending data from the US to Europe.
Yeah, US to Europe on Azure might be 2 cents a gig.
Mhm.
But if you cross certain continental divides, they hit you with massive premiums.
Like where?
Going from Google Cloud down to Asia or Australia or Azure down to South America, that can spike to 16 cents per gigabyte.
16 cents. That is double the standard internet rate. And that is just for routing your own internal traffic on their private backbone.
Exactly. It completely dictates global architecture. You can't just casually deploy a database replica to Asia to speed things up for your Japanese users.
Because the replication costs from your primary database in Virginia would bankrupt you.
Right. You have to model that 16 cents a gig.
Yeah.
There is this great breakdown from Hammy Labs in the research that illustrates this perfectly.
Oh yeah, the container comparison.
Yeah, they modeled a simple serverless app generating just 100 gigs of egress. The cost difference across platforms is wild. On DigitalOcean, it costs $1.
$1, okay.
On Google Cloud, $8.50. On Azure, $8.70. And on Railway, $10.
That is a 10x difference for the exact same amount of network traffic.
Dictated purely by the platform's pricing philosophy. And that disparity is driving two massive counter movements right now. data repatriation, and alternative clouds.
So data repatriation, that means pulling workloads entirely out of the cloud and putting them back on physical bare metal servers.
Yeah, or into leased colocation facilities.
Yeah.
People are doing the math and realizing the public cloud premium just isn't worth it for network-heavy apps.
But doesn't that mean you have to manage physical hardware again? Replacing hard drives, patching servers?
It does. You sacrifice the instant elasticity of the cloud, but the trade-off is predictable costs. Instead of unbounded egress fees, you just lease a 10 gigabit line from an ISP for a flat monthly rate.
You buy the pipe, not the water flowing through it.
Precisely.
But what about companies that absolutely refuse to go back to physical hardware? The alternative clouds seem to be weaponizing this to steal market share.
They absolutely are. Oracle Cloud Infrastructure, OCI, is a huge example in the sources. They offer 10 terabytes of free egress per month.
10 terabytes compared to the 100 gigabytes from AWS.
It is a massive difference. And even after you hit that 10 terabytes, OCI's rates are like 25% cheaper than the big three.
We also saw Latitude.Esh in the research. They offer bare metal servers bundled with 20 terabytes of free egress per server.
And then you have Fluence, which is a decentralized compute network. They have a literal zero egress model. You only pay for compute cycles and storage.
And the storage market is getting disrupted too, right?
Oh, heavily. Backblaze B2 gives you free egress up to 3 times the amount of data you store with them.
That is huge for backups.
Yeah, and they partner with content delivery networks to make outbound traffic basically free. Wasabi and Cloudflare R2 have basically built their entire brands around having zero egress fees to compete with Amazon S3.
So the key takeaway here for a CFO calculating total cost of ownership is that looking at CPU and storage prices on a spreadsheet is a trap.
A total trap. If you don't model the network traffic your app is going to organically generate, your cheap cloud migration will bleed you dry the second it goes live.
You have to forecast the velocity of the data, not just where it sits.
Exactly. But, we have to be realistic here. Ripping out your entire AWS architecture just to save on bandwidth isn't feasible for most enterprises.
Right, because you are locked into their proprietary databases or identity structures.
Yeah. So if you are locked inside the Hotel California, how do you stop the bleeding from the inside? We have to look at the internal plumbing.
Let's do it. What are the code-level strategies engineering teams can use tomorrow to patch these leaks?
The golden rule is optimizing your internal network path. And the core architectural concept here is called affinity.
Okay, affinity. Explain the mechanics of that.
So remember how moving data across availability zones costs money?
Right, the 1 cent per gigabyte toll.
Well, in a standard app, a load balancer might randomly send a user's request to an app server in Zone A. And that server might randomly query a database in Zone B.
And boom, you just crossed the boundary and triggered the toll.
Exactly. Both the query and the data coming back cross the boundary. With Affinity, you rewrite your routing logic so that servers in Zone A only ever talk to databases in Zone A.
Oh, I see. It is like taking a toll road every time you want to visit your next-door neighbor. You are just throwing coins out the window.
That is a great way to put it. You enforce strict boundaries, keep the traffic in the neighborhood.
Yeah.
You only route to Zone B if Zone A literally catches fire and you need to failover.
Just cutting out that cross-zone chatter must save thousands of dollars.
It removes millions of microtransactions from your bill instantly.
Okay, so keeping internal traffic localized makes perfect sense. But what about when our servers need to talk to the cloud provider's own managed services? Like pulling a file from an S3 bucket.
Oh, this is one of the most expensive misconfigurations in all of cloud networking.
Really?
Because by default, when your private server tries to talk to a managed service like S3, the DNS routes your traffic out to the public IP address of that service.
Wait, meaning the data actually leaves my private network, goes out to the public internet, and then comes right back into the AWS data center.
Yes. And because the packets technically touch the public internet gateway, the billing system tags it as outbound internet traffic.
So they hit you with the 9 cents a gigabyte charge for data that never really left.
It is wild, isn't it?
It feels predatory. It steps out the front door, turns around, walks back in, and you pay full price for the round trip. How do you bypass that?
You deploy what AWS calls VPC endpoints, or Azure calls private links.
Okay, what do those do?
They hijack the DNS resolution. Instead of routing out to the internet, a VPC endpoint creates a secure private tunnel directly to the service inside your own subnet.
So the packets stay on the private fiber backbone?
Exactly. They never hit the public internet, so it is vastly more secure, and it entirely bypasses that internet egress toll booth.
It is crazy that VPC endpoints aren't just the default.
I agree, but that is how they make their money.
So what about massive data pipelines? We talked about that BigQuery horror story where the daily export costs exploded.
Oh, right, the 50 gigs a day.
Yeah. When you absolutely have to move massive data sets, how do you shrink the footprint?
You have to move away from bulk processing and start doing incremental processing.
Meaning what exactly?
Well, legacy pipelines just grab the entire database, process it, and move the whole monolithic block. If it is a terabyte, you move a terabyte every single night.
Even if only a few rows change.
Exactly. The modern fix is called delta encoding. You write the logic so the system only identifies and transmits the differences, the delta, between yesterday's data and today's data.
Ah, so instead of downloading a 1,000-page ledger every night, you just download the 2 paragraphs that got edited today.
You are transmitting kilobytes instead of gigabytes. It is a massive savings.
Well, makes total.
And you also need to audit your automated replication. We see companies replicating databases to 3 different continents just because an engineer checked a box in a setup wizard.
Just burning cache in the background?
Yeah. Unless you have strict compliance rules demanding global failover, turn it off.
Okay, so we've got affinity, we've got VPC endpoints, we've got delta encoding, but eventually the data actually has to go to the customer, right?
Unfortunately, yes.
The user has to stream the video or download the update. So when we finally have to brave the public internet, how do we minimize the damage?
Well, the golden rule of network optimization is the cheapest data transfer is the one that never happens.
Which brings us to caching.
Exactly. Intercepting the request before it ever reaches your expensive cloud server.
How does that work in practice?
It works in layers.
Oh.
At the application level, you use local memory stores like Redis or Memcached.
So if 10,000 users open the app and check the daily leaderboard,
your app shouldn't query your expensive database 10,000 times. It fetches the leaderboard once, holds it in Redis, and serves the next 9,999 requests directly from local memory.
eliminating all those network hops.
And database read charges. Then, stepping further out, you have CDNs, content delivery networks.
The sources mentioned a really cool financial hack here with CDNs, the Cloudflare Bandwidth Alliance.
Yes. So we know a CDN distributes your data globally, right?
Yeah.
So a user in Tokyo gets the image from a Tokyo server, not a Virginia server.
Right, which is faster.
But financially, when the CDN pulls that image from your cloud provider the first time, that generates an egress fee.
Because it is leaving the cloud.
Exactly. But the Bandwidth Alliance is a peering agreement between specific clouds like Google and Backblaze and CDNs like Cloudflare.
Meaning they physically wire their data centers together?
Basically, they share traffic directly without using third-party internet providers. Because of that, they waive the egress fees.
Wow, so if you route your traffic through an alliance partner, you can literally zero out your cloud egress bill.
It is a massive structural hack to bypass the toll booth entirely.
That is brilliant for static files. But what about massive dynamic workflows? The research had this brutal use case about video editing teams using LucidLink.
Oh, video production is the ultimate stress test for cloud economics.
Because the files are huge.
Massive. The traditional model is sync and share, like Dropbox. If you have 5 remote editors working on a 500 gigabyte documentary, every time someone makes a change, that massive file has to sync to everyone's local drive.
If they do that twice a day, the network costs would be insane.
It would eclipse the storage costs in days. The architecture just doesn't work with egress pricing.
So how does LucidLink fix it?
They ban downloading entirely. They use a pure byte-level streaming protocol.
What does that mean for the editor?
The software mounts the cloud bucket like a local hard drive. But here's the magic. It only streams the exact, specific bytes the application is asking for in that exact millisecond.
So if I'm scrubbing through a timeline, I'm not downloading the whole hour of footage.
Nope. It is dynamically fetching only the specific frames your playhead is touching. You turn a 500 gig bulk download into a targeted multi-megabyte stream.
That is so smart.
And they take it a step further with localized caching nodes. They have this feature called Team Cache.
How does that work?
You put a physical cache server right inside the Office network. So Editor 1 streams a clip from the cloud, and it instantly caches locally.
Ah. So when the other 4 editors view that same clip, it pulls from the local server.
Exactly. Bypassing the cloud entirely, it completely eliminates repeated egress for the same video.
It is like building your own micro CDN in the office.
It really is.
Okay, so we've covered caching and streaming to stop data from moving. But what about the data itself? Can we just make the payload smaller?
Yes. Payload reduction is the lowest hanging fruit that teams just constantly ignore.
What is the easiest win?
Just Turning on standard web compression, gzip or Brotli. Just configuring your servers to compress text-based data like HTML or API responses can shrink the payload by 70%.
That is an instant 70% discount on that traffic.
Achieved by changing a few lines in a config file.
Yeah.
It is that easy. But you also have to look at how your internal microservices talk to each other.
The sources mentioned JSON being a problem here.
Developers love JSON because it is human-readable and easy to debug. But structurally, it is incredibly bloated.
Why is it bloated?
Because JSON sends the structural keys with every single payload. So if you send 10,000 user profiles, the strings for first name and last name are repeated 10,000 times across the network.
Oh man, that is so much wasted bandwidth.
Right. So the fix is switching high-volume APIs to binary serialization formats like protocol buffers or protobuf or Apache Avro.
Because protobuf uses a schema, right?
Yeah.
Both servers already know the blueprint.
Exactly. You don't send the string first name, you just send the raw binary data mapped to field index 1.
And the payload size just plummets.
And your egress costs drop right along with it.
Speaking of making things smaller, let's talk about video compression, because the sources dive deep into the AV1 standard.
Well, video is the vast majority of all internet traffic, and the AV1 codec is a generational leap. Compared to the old H.264 standard, AV1 gives you up to 40% bandwidth savings with the exact same visual quality.
40% savings on video is a game changer. So why isn't everyone using AV1 right now?
Because the math to compress it is really complex. It used to require massive CPU power to encode and decode, making it too slow for real-time stuff.
Ah, so it was a hardware bottleneck.
Yeah, but we have crossed the inflection point. Modern silicon, from high-end GPUs down to your smartphone, now has dedicated AV1 hardware acceleration built in.
So the big players are adopting it?
Oh, Netflix and YouTube are pushing it aggressively because it instantly slashes their biggest operational expense.
Which brings us to a really fascinating pivot in the deep dive. If AV1 saves 40% on video, what if we just didn't send the video to the cloud at all?
And this is where we get into industrial IoT, which completely flips the cloud model on its head.
There is this great story from an engineer named Prasad Bond. He talks about the industrial cloud bloat problem.
It is such a vivid example.
He describes these factory CTOs who are spending thousands of dollars a month to stream continuous 4K video of perfectly normal functional conveyor belts up to the cloud.
Right, because they are using AI for defect detection.
Yeah.
They want the cloud model to flag if a widget is scratched or missing a piece.
Which sounds like great modernization, but Prasad points out the absurdity. 99.9% of the products on that belt are totally flawless.
Exactly.
So they are paying massive ingestion fees, upgrading their fiber networks just to stream endless hours of empty, normal footage.
It is pure architectural bloat. They are paying a huge premium to transmit data that has zero business value. The value is only in the anomaly.
So if moving the data to the brain is too expensive, we move the brain to the data.
Exactly. That is edge computing, or fog computing as it is sometimes called.
How does that actually work mechanically?
Instead of sending the video out, you put an Edge-Inference node right on the factory floor, like a rugged NVIDIA Jetson module plugged directly into the camera.
So the AI runs locally on the edge device.
Yes. It watches the 4K stream locally. It consumes zero internet bandwidth.
Incredible.
And when it spots a scratched component, it just isolates that one frame. It sends a single 500 kilobyte JPEG, a timestamp, and some metadata up to the cloud dashboard.
So it turns a continuous 4K stream into a single 500 kilobyte image.
It is the ultimate physical compression. It drops the bandwidth requirements by over 99%.
That is brilliant. But operationally, managing hundreds of physical edge computers all over the world sounds like a nightmare.
It would be, but the cloud providers adapted. They now provide the orchestration for the edge. The sources talk about the AWS stack for this, SageMaker Neo and IoT Greengrass.
Okay, so if I have this massive resource-heavy AI model in the cloud, how do I fit it onto a tiny factory sensor? Does SageMaker Neo basically prune it down?
Yeah, that is a great analogy. It is a compiler. It takes the bloated cloud model and mathematically optimizes it, stripping out all the unnecessary parameters so it runs fast on local silicon.
It shrinks the brain to fit the skull.
Exactly. And then AWS IoT Greengrass is the runtime that sits on the physical device.
What does Greengrass actually do?
It lets the central AWS cloud securely push that compiled model down to the factory over the air. But more importantly, it manages the execution.
Meaning if the factory loses internet.
The AI keeps running, it processes everything offline, patches the anomaly data, and sends it securely once the connection's back.
So the cloud just becomes the command center for a decentralized fleet. That is fascinating. But whether you are managing edge devices or complex cloud microservices, you have to be able to monitor it.
Oh, absolutely. Governance is everything.
Because if you don't have visibility, the finance team is still going to have a heart attack at the end of the month. Let's look at Kubernetes and FinOps.
We have to start with Kubernetes. It is amazing for orchestrating containers, but its core design makes it incredibly dangerous for hidden egress fees.
Why is it dangerous? Is there a flaw in the architecture?
It isn't a flaw, really. It is how it was designed.
Hmm.
Google built it for internal infrastructure, where internal network costs didn't matter. So by default, Kubernetes networking is totally flat and permissive.
Meaning any pod can talk to any other pod.
Freely. Because microservices need to chat. But when you put that cluster in a public cloud across multiple availability zones.
That chatting suddenly crosses billing boundaries.
Exactly. A pod in Zone A constantly syncing with Zone B turns into a silent, continuous toll booth.
That sounds like a nightmare.
It gets worse. People constantly misconfigure NAT gateways.
Network address translation, right? To let private stuff hit the internet.
Yeah. If a pod in a private subnet tries to hit an external API or even another managed cloud service, if they didn't set up VPC endpoints, it goes through the NAT gateway,
Which translates the address, sends it out to the internet, and brings it back.
triggering outbound data charges for internal chatter.
So how do DevOps teams actually fix this?
You have to move away from the permissive model and implement a default deny network policy.
Just lock everything down.
Lock it all down globally. Then carefully whitelist only the exact communication paths the application actually needs.
But the sources highlight a massive trap here with DNS resolution, right?
Yes. If you implement a blanket default deny policy, you will instantly break your entire cluster if you forget to leave DNS port 53 open.
Because if the pods can't do a DNS lookup, they can't find anything.
Right. You secure the perimeter, but keep port 53 accessible. And beyond policies, you need granular visibility. You can't just use standard cloud bills.
Because standard bills just say data transfer, $10,000, and give you zero context.
Exactly. You need tools like KubeCost or OpenCost. They hook into the Kubernetes API and map the network usage to specific units.
So it tells you, like, the new AI pod spent $8,000.
Exactly. It enforces accountability. But, attribution just tells you who spent the money. It doesn't tell you how or why.
Which is where OpenTelemetry comes in, right? The sources push this hard.
Yeah, AWS distro for OpenTelemetry with Amazon Managed Grafana. OpenTelemetry gives you distributed tracing.
Walk us through how that actually stops an active leak.
Say an engineer pushes an update, and suddenly egress spikes. Without tracing, you are totally blind. But OpenTelemetry attaches a unique ID to every single user request.
So you track the requests through the whole system.
Exactly. Through the load balancer, into the pod, querying the database, you can see that a new microservice has a runaway loop.
Like it is polling a 5 megabyte payload every second instead of every 5 minutes.
Exactly. The trace lets you pinpoint the exact pod, sometimes the exact line of code, so you can kill it immediately instead of waiting for the monthly bill.
Speaking of the bill, we need to give the finance folks a framework for forecasting, because predicting egress feels impossible.
It is chaotic, but you can control it with FinOps. And that starts with merciless tagging.
Tagging everything.
Every S3 bucket, every EC2 instance, tag it with Cost Center, Finance, or Project Alpha. The rule is, an untagged resource is an unauthorized resource.
So if a developer deploys something without a tag, the pipeline just kills it.
Exactly. That stops the corporate finger pointing. But you also need aggressive billing alarms.
Don't wait for the end of month post-mortem.
Right. Set an alert at 50% of your projected spend. If someone deploys a rogue loop on Friday afternoon, that 50% alarm goes off Saturday morning, giving you time to intervene.
Instead of coming in Monday to an incinerated budget. And the last piece is predictive modeling, right?
Yeah, aligning engineering with finance. If you are launching a major feature, users are going to explore the UI, which spikes API polling. You have to forecast that.
Or if you were doing a massive DR drill.
You have to mathematically model the network cost of restoring those terabytes before you authorize the test.
You can't manage what you refuse to measure. Egress is so sneaky. It hides in background syncs, chatty microservices, uncompressed JSON payloads.
But if you architect for efficiency, use peering agreements, deploy Edge AI, enforce default deny policies, you can dismantle those tool booths.
And it is not just about saving money. It is about architectural freedom. When your team isn't terrified of data transfer costs, they can build resilient multi-region global apps.
It removes the biggest artificial constraint on innovation.
Absolutely. But before we wrap up, I want to leave you, the listener, with a provocative question to think about. We've talked about surviving the current cloud model, but that model is getting violently shaken up by generative AI.
The data gravity requirements for large language models are just unprecedented.
Exactly. Training these models demands petabytes of data. So the question is, will the crushing weight of this AI data gravity fundamentally break the public cloud's legacy egress pricing?
Because companies physically cannot afford to move petabytes of training data in and out of the big clouds at these prices.
Right. Will we see a massive swing back to on-premise bare metal data centers, just so companies can actually converse with their own data without paying a toll on every syllable?
It is a massive structural tension. The
Got it.
physics and the economics are on a collision course. Something has to give.
It is going to be fascinating to watch. The egress landscape is incredibly complex, but by mastering the mechanics we talked about today, from routing tables to AV1 codecs, you can stop the hemorrhage. Keep questioning the default settings, scrutinize your network paths, and stay curious. Thanks for joining us on this deep dive.